Sorry.
Should I restart or just continue?
Yes, you may continue.
Okay. Yeah, so tomorrow I'll talk about some applications of information theory and communication complexity. On Wednesday, I will say something about why communication complexity is so important and what we can do with the results in communication complexity. And then finally, on the last day, I'll switch gears to discussing a quite different topic. I'll talk about interactive coding. So what can you say about how to recover from errors when you have an interactive conversation between two parties, rather than what's studied traditionally in coding theory, which is just sort of a one-way conversation. Okay. So that's a broad outline of what I'll talk about. So I'm writing a textbook on communication complexity with Amir Yehudarov. And if you go to my webpage, you will see a link to a draft of the textbook. It's still probably many months or maybe a year away from completion. But if you want to learn more about what I'm going to talk about, if you want to dive in deeper, then I think that's a good resource. And there are also videos of other lectures that I've given on my webpage that you can look at. Okay, so what is communication complexity? So communication complexity is about this really basic question, just stated not in terms of math, but as a sentence. If you have a group of people and they want to have a conversation in order to understand something, then how long does that conversation need to be? It's roughly what we want to try and understand. How long does their conversation need to be in order for them to accomplish their goal? Earlier today, this morning, we saw some examples of where communication complexity is interesting, but there are sort of many settings where this question shows up. And what I'm going to try and show you is sort of how to make a theoretical framework to understand this kind of question. So I should say the area was first formalized mathematically by Andy Yao, but it's since then become quite important in computer science. And communication complexity has had quite a success story in the last 20, 30 years, and that's kind of because of how it fits in our understanding of many other things. So on the one hand, it has this really nice feature that the mathematical model of communication complexity is really easy to understand. So it's really simple, it's really clean, and that means that all kinds of ideas from mathematics, from information theory, have something to say about communication complexity. Okay, so it's easy enough to understand, and it's simple enough that many different ideas from mathematics can be used to say something useful about it. On the other hand, it's also general enough that when you do understand communication complexity really well, you can leverage that understanding to understand many applied questions. So many questions about, usually about other computation models or other computational systems. And so that's you know, this side of the picture, it sort of keeps getting bigger and bigger. So when communication complexity was first invented, there were only like 3 arrows here. But it seems like every 10 years, there's a whole new area that suddenly realizes it can use ideas from communication complexity to understand their own area. So that's, for me, big evidence that this point in the picture is really important. It's, in a sense, a way to connect these really basic ideas in mathematics to places, to sort of diverse applications. Okay, so that's why I view communication complexity as a fundamental theory. So one reason why communication has had so many applications here is because sort of inherently it's hard to imagine any model of computation that does not involve communication. So when you think of computation, whatever model you come up with, I'm pretty sure that you will somewhere involve some kind of communication. Okay? And that's kind of why communication complexity has played such an important role. And I want to start by just giving you a really nice example. It's actually maybe the first example where communication complexity was used to prove a lower bound, just to show how that can happen. So here's sort of the initial example for how you can use communication complexity to prove a lower bound. So people in the late 70s were trying to understand VLSI chip design. Okay, so the problem they were faced with was they're trying to make digital circuits, right? And so this is a picture of a digital circuit. And the way you have to do that in practice is you got to lay out components, right? So you have this piece of silicon, and you have to design, and you want to compute. You want this chip that you're going to design to compute something, this function f. And in order to compute it, you have some number of inputs that are relevant to f, and you have to somehow combine these inputs to figure out the value of f, right? So you design sort of, so what's written here, there's some locations where you have inputs, and then you have some sort of boxes that do computation, that take two or more inputs, and then combine them to compute something. And somehow this entire network together will compute f. Okay. So say you design such a chip that computes some f, it's going to go into your computer. And now you want to know, is the design you came up with the best design? Right? Is that the best idea for how to compute f? And that's kind of a hard question to figure out. Right? Maybe there's some other way to compute f that gives you a better chip. So in this context, the thing you're trying to optimize is the area of the chip. So the smaller the area of the chip to compute f, the better. Because that means that you'll compute f faster, and it'll be cheaper to make the chip. Okay. So how do you know that the design you came up with is the best possible? And here's the idea that Thomson in the late 70s came up with. So you notice this. Suppose you took the chip and it had area A. Then no matter how you design the chip, how you put the components on it, you can always find a way to cut the chip into two pieces so that the number of wires it crosses from one side to the other will be at most the square root of the area. Okay? And that's just comes from the geometry of laying out components on a chip. So like in this example, there's this cut that divides the chip into two parts, and only two wires are crossing the cut. Only two wires are going from that side to this side. And that means that if you can now prove that the communication, so now you can imagine that what's really happening here is there are two people. One person knows all the inputs on this side, all the x's on this side. One person knows all the inputs on that side. And they're able to compute f by just communicating the contents of two wires. So involved in this design is a very cheap communication protocol, a very small conversation that computes f. And so if you can show that there's no such small conversation, so if you can show that, for example, to compute f, you must communicate, say, omega n bits, then you basically have proved that no matter how you design the chip, you have to use area n squared. So my main goal in showing this example is just to show that, ahead of time you would have looked, maybe if you thought about this problem, it might seem like there's nothing about the conversation between two people involved here. But if you know something about how much communication it takes to compute f, you can prove things about even a computation model that looks quite different. Okay. All right. So what I will do now is, can I raise the? So feel free to ask me questions about anything as I go. So my plan for the rest of today is my aim is to eventually just tell you about what the model, what a conversation exactly is, what a mathematical model is to define a conversation and measure the communication complexity or something. But the way I'll do that is I'm going to start, we all have a pretty good idea of what a conversation is. We do it all the time. So I'm going to start just by giving you some examples without formal definitions. So I'll show you some clever examples of sort of clever protocols for conversations that I know of. And then after we see these examples, we'll discuss a formal definition of what a communication protocol is and how to measure communication. That's what we'll do today. Okay, so I'm going to start by just giving you by discussing 3 communication problems. Okay, so so feel free to interrupt or slow me down if I go too fast.
Since this part will be written, may I suggest people at the very back may consider moving down?
Yeah, that's a good idea. Yeah, so the rest of my lecture will be on the board. All right. Okay, so the first communication problem I'm going to discuss with you is actually all the ones I will discuss today involve 2 people who are trying to communicate with each other. Although you can study more than 2 people also, and they're very interesting results in that setting as well. So the first problem I want to talk about is a beautiful problem of that was solved by Ho, Ullman, and Yannakakis. And that's the cliques versus independent sets problem. So let me set it up. So the setup is you have a graph. Okay, so say you have this graph Q. Has some vertices. Okay, so some graph like this. And so let me just remind you, a clique in this graph is a set of vertices that are all connected to each other. For example, this set have 4 vertices. This is a clique. And an independent set in the graph is a set of vertices that does not contain any edges. Okay, so this set of vertices, there's no edge going between any 2 vertices, so this is an independent set. Okay. So let's say there are n vertices in total. So here's the problem. So the setup is you have 2 parties, Alice and Bob, and they both know the graph G. Okay, so they know ahead of time that there's this graph G, and this is they have this ahead of time, and then Alice gets as an input a clique. Okay, so Alice gets a clique. And Bob gets as input some independent set. Okay. So Bob knows an independent set in the graph, and Alice knows the clique. And what they want to understand is, is this clique, are these 2 sets, are they disjoint or do they intersect? they want to know, is there a vertex that's in both of them? So is there a V that's in both the clique and the intersect and the independent set? This is what they want to know. Okay. Okay, so now of course, if someone knew what such a vertex was, then it would be easy. If someone told them, there is a vertex and here's the name of that vertex, then they could both very quickly check that vertex is in both their sets. Okay, that would be, and they could just verify that very quickly. But because Alice doesn't know exactly what the independent set is and Bob doesn't know what the clique is, they need to exchange perhaps a lot of information to figure out if there is this common vertex in the clique and independent set. Okay. So maybe a trivial idea, a trivial protocol. Maybe I'll ask someone. So can anyone tell me what's just a trivial protocol to solve this problem? Send all of them. Yeah. So Alice can just send the clique, right? So Alice can just send C to Bob. Now Bob knows both the clique and the independent set. And Bob will say whether or not there's a vertex in common. Just 1 second. And this will take, in general, n bits of communication, right? Because C is some subset of these n vertices. So to describe a subset of n vertices, there are 2 to the n possible subsets. So to describe such a set would, in the worst case, take n bits. Yeah?
Sorry, just in the model, you require either party to solve the problem. You don't require either both or a verifier.
Great question. So what I'm going to require is that at the end of the protocol, both should know the answer. Okay? So I'll define that formally later, but in words, what I'm going to require is actually that after they see the messages, they both know the answer to this question.
If anyone knows the answer, he can just simply transfer the message.
Exactly. If Bob figures out the answer, he can send 1 bit to Alice to say yes or no. So that just changes it by 1 bit. Okay, so technically, I should say that Alice sends the clique, and then Bob should send 1 more bit to say whether or not there is a vertex in common. And this would be a protocol that solves this problem. Okay, so that's the. Is the problem clear? Maybe you should keep me posted about how I'm doing on time, because I'm not sure when I'm starting now.
Okay,
Okay, tell me in the halfway mark. Okay, so this protocol, it takes n bits. What I'm going to show you is a really clever protocol. You can actually solve this problem with log squared n bits of communication. Okay, and so that's what they figured out. So there's a protocol with log squared. I'll just show you the protocol. It's going to take log squared n bits of communication. And in fact, we know today, it was just proved a few years ago, that this is the best you can do. Okay, so somehow the right number of bits, the best you can possibly do is log squared n bits of communication. So I'll show you the protocol. It's really beautiful. So the basic idea is they'll do the following. So our protocol. If it's a case, suppose there's a vertex V in the clique such that V has more than n/2 neighbors. Less than n/2. Then Alice will send V to Bob. Then Alice is going to send V to Bob. Now this step is quite cheap. To describe a single vertex in the graph only takes log n bits. There are n vertices in the graph. This is log n bits. And this vertex is actually very, very useful to Bob. Why is it useful? Because, say V is like this, and it has few neighbors, right? It has only n/2 neighbors. But V is a member of the clique. So that means the clique can only be a subset of this set of vertices, right? So all the other vertices are completely irrelevant to the problem. Bob can just throw them away. So what will happen is that Bob will throws away the non-neighbors of V, which is roughly half the vertices in the graph, because V has only at most n/2 neighbors. So Bob throws away at least half the vertices in the graph. That's a lot of progress. Of course, if V is in Bob's independent set, then we're done. So they might get lucky, and V might actually be in Bob's independent set. In that case, they found the answer, and Bob will say, this V is in my set too. So they intersect. In the same way, if there's a vertex V that's in the independent set that has lots of neighbors, has more than n/2 neighbors, then Bob is going to send that vertex to Alice. Okay, and again, this only takes log n bits of communication. Only takes log n bits to describe V. And now Alice has learned a lot, because all the other vertices of I have to be non-neighbors of V. So Alice can throw away all the neighbors of V. Alice throws away the neighbors of V. And they continue the protocol. Okay. So this is what they do. So in each step, if there's such a vertex, Alice sends something to Bob. If there's such a vertex, Bob sends something to Alice. And they try to do this until there's no, either they'll find an intersection, okay, or either they'll find a V that's in both of their sets, or both of these conditions will not be true. So what can you say if there is no vertex like this and no vertex like this? Alex knows the answer. Anyone? So there's no vertex like this. So every V in the clique has more than n/2 neighbors. Yeah, some. Sorry? You're okay with whispering the answer. Okay, so I'll repeat what you said. So, if neither happens, that means all the vertices in C, they have more than n/2 neighbors. All the vertices in I have less than n/2 neighbors. So there cannot be any vertices in common. So they're done, right? They know that there's no vertex that's in both sets. So if neither this happens or this happens, it means that the clique and the independent set must be different. They have no vertices in common. So if neither, then the clique and the independent set are, the intersection is empty. Okay. So that's a protocol, and how much communication does it take? Well, each of these steps, anytime someone announces a vertex, that takes log n bits. But every time they do that, they reduce the size of the graph by half. They reduce the number of vertices by half, effectively. So the number of such announcements can be at most log n. After you've announced log n times, then the graph is gone. Because every time you're cutting the graph, the size of the graph down by half. Okay, so the number of iterations can be at most log n iterations. And that means the communication complexity, the total number of bits that will ever be sent by this protocol is 4 log squared n. So it's a really nice protocol, and one of the things, it's nice for many reasons. We'll see later that actually it says something quite general about all communication protocols. But another nice feature of this problem is that it really shows you that interactive communication is much more powerful than non-interactive communication. In fact, you can show, suppose we were going to do this with just one-way communication. Suppose we were going to say that Alice will say something to Bob, and then Bob will say the answer. Then you can show that there's really nothing you can do better than this. You cannot do much better than n bits. Okay, there's no way to save on the communication over just a trivial idea. But if you allow both parties to speak, and you allow them to listen and respond to what the other person is saying, then that gives you a lot of power. Then you can actually get conversations that are much shorter. They're almost exponentially shorter. Okay, and so that's a sign that somehow interaction is really powerful. So what is my time? Okay, so that's a nice protocol. And next, I want to show you a couple of protocols that are randomized. So another thing that's true about communication is that the availability of randomness really helps increase the efficiency of communication protocols. And I want to show you that with a couple of examples. So the first example is the equality function. So what is the equality problem? So here Alice and Bob are given n-bit strings. So Alice is given x, that's an n-bit string, and Bob is given y, that's an n-bit string. And they want to know whether these two strings are equal or not. Very simple. They just want to know, is x equal to y? So again, just like there, the trivial idea is, Alice sends her entire string to Bob. This takes n bits, and then Bob can say whether they're equal or not. That takes one more bit. So you can solve this problem with n+1 bits of communication. But what I'm going to show you is that if you're allowed to use randomness, then you can solve it much more efficiently. In fact, with a constant number of bits of communication. And since I assume that many of you like error-correcting codes, I'm going to use error-correcting codes to solve this problem. So let me just remind you what is an error-correcting code. So an error-correcting code is a function E that maps. What I'll need is something that maps the n bits to. So I'll use a larger alphabet. So it's the worst sigma I ever drew. To n symbols of some larger alphabet. Think of it just as a constant size alphabet, with the property that if x is not equal to y, then e of x, the encoding of x, and e of y disagree in, say, 2/3 of their coordinates. So we know how to make such functions. So you just want the distinct strings x and y, distinct messages should be mapped to code words that are far apart in Hamming distance. In this case, I want them to have relative distance at least 2/3. And how is the code useful? Well, here's how you can use them in a randomized protocol. So Alice and Bob want to know, are x and y the same, right? But they don't want to communicate a lot of bits. So what they can do instead is, what they will do is they will sample a random coordinate I in M, and they will do this at random. So they'll sample a uniformly random coordinate of the code word, and then Alice will just send the ith coordinate of the code word. So she has x. She'll send e of x of I to Bob. And then Bob will just check whether or not this is consistent with the ith coordinate of his code word. Bob will just check e of x of I equals 3 of y of y. This is what he'll check. And if they're equal, Bob will assume that it must be that x and y are the same. If they're not equal, he knows for sure that x and y are not the same. So he'll just respond yes or no. So the end result is you have a communication protocol where the number of bits communicated is only a constant. And it doesn't always give you the right answer, but the probability of making a mistake is at most 1/3. Because when do you make a mistake? You make a mistake when x and y are not the same, but you were unlucky in finding a coordinate in the code word where the two code words were the same. But the probability of that is small. It's only 1/3. So the probability that this protocol makes an error is only 1/3. So somehow it's a kind of interesting application of error correcting codes because there are no errors here, right? We use the error correcting code just to save on communication. The error of the code went into sort of the error of the protocol, but it's not like there's an adversary corrupting. Another interesting feature of this protocol is that actually, if you're not allowed to use randomness, if your protocol is deterministic, then in fact you can show that there's nothing better you can do than the trivial protocol. You must send n bits. Okay, so somehow by allowing randomness, we went from the best protocol taking n bits to the best protocol taking a constant number of bits. If you allow randomness and errors. Yeah. Good question. So you can model a randomized protocol in two ways. You can count two things. You can count how much randomness you used and how much communication you used. And usually in communication complexity, we count the communication, not the randomness. But you're right. If I wanted to count the randomness, then it would be, so maybe we don't have sort of this shared random string. But then even then it's still pretty cheap because if we didn't have this, Alice could sample I and send I, but that would be only log n bits. So that would still give you, something much better than doing it deterministically. Yeah, and in fact, you can show that actually for any randomized protocol, if you assume shared randomness or you don't, the difference between those two models is only log n. Okay, so actually this log n is not just for this problem, but for any problem, if you want to take shared randomness and simulate it with private randomness, you can do that with just a log n over n. So it actually is not a big difference in the models. Any other questions? Yeah.
So does Alice of Bob know if the protocol failed?
They don't. Yeah. So in this case, yeah, they don't know, and they have to just take the outcome and live with it. There's some chance that the protocol failed. So that's yeah.
Then how do you solve that problem?
It's impossible to solve that problem. So if, for example, if you had a randomized protocol where you're sure that the answer is correct, then actually you could just make a deterministic protocol out of it. Okay, so in order to get such an efficient protocol, you have to have accept that with some probability the protocol will fail. But it's not so bad because this probability of failure, you can drive it down to be arbitrarily close to 0. I could make it 10 to the minus 6 by increasing the communication by a little bit. Okay, so you can make it so unlikely that it's safe to do. Any other questions? What's my when am I supposed to end? 2:30. Okay, so that's a randomized protocol. And now I want to show you another randomized protocol. That's a much more clever one. This one I won't analyze so much, but I think it's a beautiful protocol, so I just wanted to show it to you. So this is the problem of k disjointness. And the protocol I'm going to show you is using Hassad and Wigderson. So the problem, again, it's a very simple setup. So Alice and Bob are going to have two sets, sort of just like in the clique versus independent sets problem. So Alice has a set X is a subset of the numbers 1 through n, and Bob has a set Y that's a subset of the numbers 1 through n. And in addition, they know that the size of the sets is at most k. So X and Y, you think of them as small sets. So they're sort of this large universe, and X and Y are two small sets coming from that universe. And what they want to know is, are the sets disjoint or not? So is there D in the intersection? So what you can show, so as usual, there's the trivial protocol, right? Alice sends her set to Bob. And the trivial protocol, how much communication does it take? It takes as much communication as is required to describe a set whose size is at most k, okay, which is it's this number, log of sum I equals 0 to k of n choose I. Okay. And in fact, you can show that if you are restricting yourself to deterministic protocols, then this is the best you can do. There's nothing you can do besides this protocol. Okay? This number is actually exactly tight. You cannot even save one more bit than that. But if you're going to use randomized protocols, so maybe I should, this is hard to understand, so let me just write what this is. This approximately you can think of for k small is like k log n over k. Take my word that that's true. That's like k log n over k. And Hassad and Wigderson found this protocol that uses randomness, and the communication is going to be only order k. So we will shave off this log term using randomness. So let me describe that protocol for you. So here's how it works. So the randomness is going to be a sequence of random sets. So Z1, Z2, and so on, which are all uniformly random subsets of 1 through n. And what Alice and Bob are going to do is Alice is going to send an index j to Bob, where j is the smallest index with x contained in zj. So Alice will find in this random sequence of sets, what is the first set that completely contains my set? And she will send Bob the index of this set. Now, what is the point of doing this? Well, if you look at the picture, so suppose this is x. Suppose x and y are disjoint. Suppose x is here and y is here. Then what will this zj look like? Well, zj is going to contain x, but that's the only constraint on zj. So zj is sort of going to look like a set that contains x and then a random subset of the rest of the universe. And the point is, if Bob knows zj, he can then immediately throw away all these elements. These elements cannot be in x. So Bob will just throw away this. Okay, and this typically is a lot of progress because you would expect sort of half of Bob's set to be thrown away. If it's destroyed, then zj is going to eliminate, on average, half of Bob's set. And that's the key idea of the protocol. So Alice does this, and Bob will do the symmetric thing. He will send j prime such that j prime is the smallest index with y contained in j prime. And they will just repeat this process. So it turns out, so sending j will, you can argue that it's going to typically take about k bits to meet j. But after you do that, then the half of Bob's set will get chopped off. And Bob will do the same thing with j prime, and then half of Alice's set will get chopped off. So what they'll be left with is a problem where k is reduced by a factor of 2. And if you keep repeating this and you measure the communication complexity, you get a geometric sum. The overall communication will be bounded by k. So it's a really simple protocol and not too hard to analyze. But again, using this randomness saves you something over the deterministic, the best possible deterministic protocol. Okay. Yeah.
So if you wanted to implement the same with just private randomness, could you still do it with log n?
Yeah. You could still do it with log n. But it wouldn't be so nice to describe. Yeah, so you can transform any protocol. So this has a huge amount of public randomness. But by what I said earlier, you can do it with just log n with the public randomness. But the transformation to do that would make the protocol very ugly. So let's stick with the beautiful but expensive protocol. More questions or comments?
How many Z's do we have?
An infinite number. So this is just for a mental experiment.
Then how do we know? How do we know using k-bits is sufficient to transmit the index? Okay.
The expected number. So okay. So if I want to formally analyze this, then what you can show is that the expected number of bits is k. Okay, and then you can use Markov's inequality to argue that with high probability it will be 100k. So if the communication exceeds 100k, you just abort the protocol. So there's some probability of error, but the probability will be small. More questions or comments? Yeah, so this is more of a proof of concept. So if I was actually going to implement something like this, then you wouldn't want to sample this infinite list. But you can, once you know that this is possible, then there's a way to convert it to something that's more meaningful with finite things and still works with the same performance. Okay, so those are the three protocols that I wanted to describe to you. And now what I want to do in the remaining time is, so I think you all have a pretty good idea of what a protocol is because we all understand these examples. But to really reason about it, we need a mathematical definition for what is a communication protocol. It should be one definition. So that's what I'll just try to tell you. I don't want to get bogged down in details, but I'll tell you what that definition is and prove and tell you one very useful property of the definition. So what is a communication protocol, or how should we define it? Of course, I just want to say, so just like in computer science, you ask me what is a program, I can tell you the definition of a Turing machine. Okay, but then if you're going to actually write a program, you're not going to think about Turing machines. That would be ridiculous. In the same way, when people are designing protocols, you think like this. Right? But you still need a definition to make sure that you're all talking about the same thing. Especially if you want to prove lower bounds. If you want to say there's no possible protocol that can achieve something, then we definitely need a definition for what a protocol is to reason about all possible protocols. So what is a protocol? So here's how it's defined. So a protocol is defined by a binary tree. So in general, the setup, as we've seen, for two parties, Alice has X, Bob has Y, and they want to exchange messages. Okay? So what is a protocol? A protocol should somehow describe how, what messages they will send, who will speak, and so on. So how can we define that? We'll do it with a binary tree. It's a rooted tree. And every node in the tree is going to be associated with one of the parties. Okay? And we'll have a function of that party's inputs. For example, this node A is going to be associated with the function pi sub A of X. Okay, this indicates that in the start of the protocol, the first bit will be sent by Alice. And the bit that will be sent by Alice will be exactly pi A of X. Okay, so there's a function mapping Alice's inputs to the bit that she will send. And that's true for every node in the protocol. So this node in the protocol is going to be associated with this function pi b of, say, y. Here, pi c of bx. Okay. So that's all the way down. So the tree continues like this all the way down. And every node is associated with a function that depends on only one of the party's inputs. And when they execute the protocol, what they do is they start at the top. Say it's pi a of x. So Alice will send the bit pi of x to Bob. And then they both move to the corresponding child of the root. So if the evaluation here was 0, they go to the left. Now they're at this node. Now this node is labeled by a function of Bob's input. So Bob will evaluate pi b of y and send that bit to Alice. So Bob will send the second bit of the protocol, and then say that's a 1, they will go to the right, and then continue. Okay. So in this way, the execution of the protocol, they're sending messages and taking a walk in this tree. Okay. And they stop the protocol when they reach a leaf of the tree. And that leaf of the tree is the outcome of the protocol. Presumably, once they reach the leaf, if the protocol is correct, then that leaf should determine the answer to the question that they were trying to ask. So that's a communication protocol. And the communication complexity of this protocol is just the depth of the tree, because that's exactly the number of bits that they will send in the worst case. So the depth of this tree is the communication complexity.
In the first step, Alice is to send one, then Alice computes another function.
Yes. So maybe the protocol involves, like here, Alice is going to send a very long message, log n over k. So log, k times log n over k. So that'll mean that actually all of the top part of the tree is labeled by Alice's bits. So it'll be the first bit of the encoding of x, the second bit of the encoding of x, third bit, so on all the way down. And then at the end, Bob will send one bit. But in general, it might be that, so this allows you to sort of basically define all protocols that you might imagine. In every step, for each bit, they should both be clear on who's speaking, who's supposed to speak, and they just send one bit. But that doesn't mean that in practice, they can still send long messages. And that'll just mean that they're taking many steps in the tree in one go. More question. Yeah. These are deterministic protocols, yes. Yeah. And a randomized protocol is just a distribution on such things. Okay, so a randomized protocol, as I've defined it with shared randomness, just means Alice and Bob know some distribution on such protocols. They pick one publicly or with shared randomness, and then once they have that, it's a deterministic protocol that they execute. That's a randomized protocol. Okay, so there's one more thing I want to do in the remaining time, which is I want to show you a nice picture to understand, now that we have this definition, you can draw a nice picture about what a protocol is really doing. At least for two-party protocols, you have a nice picture. What is the protocol doing? So let's draw this picture of the space of all inputs. So Alice and Bob, say they have some inputs and they have some protocol that they know ahead of time, they're going to execute that protocol. Let's see what happens to this picture. So here I'm going to draw a matrix that has rows indexed by x and columns indexed by y. So every row of the matrix corresponds to Alice's input, and every column of the matrix corresponds to Bob's input. And let's say we would label the input they care about. So this is the xyth entry. This is what they want to compute. So you can think of what they're trying to compute as an entry of this matrix. And Alice knows the row, and Bob knows the column. And this is what they want to compute. They want to know what is this entry. So that's, in general, basically I've drawn the truth table of the function that they're trying to compute. Since there are two inputs instead of a table, it's a matrix. So what happens when they run such a protocol? So first, Alice sends the first bit, right? And you can think of that as Alice is sending some information about a subset of the rows. So there's some way to partition the rows into two sets with the property that, say, for these rows, Alice would send 0, and for these rows, Alice would send 1. So you can think of the first bit as partitioning the rows into two sets. And then, say Alice sends 0 here, then Bob would send the next bit. But that means that Bob will partition the space of inputs into two pieces. Okay. So after Alice sends this bit, if Alice sends 0, then Bob knows, both Alice and Bob know the input they care about is somewhere in this region. So then Bob sends another bit, and that partitions the columns. and so on. So you can think of what the protocol is doing is partitioning this picture into these rectangles. In each step, they have a rectangular region, and one of them announces some information which partitions that region into two pieces. And they now know that the point they care about is in one of those pieces. But always the potential set of inputs that they're working with is a rectangle. And you can prove that. I won't prove it. But that means that when the protocol terminates, okay, so suppose this is, if we now go and look at all the regions that correspond to the leaves, each of those regions is a rectangle in this picture. And if the protocol is correct, it means that once you reach the end of the protocol, you know the value that you're after. So it better be the case that, suppose all of this region led to the same leaf, the value of the function must be a constant in this region. Because when they get to here, they stop running the protocol and they output an answer. So that means all of the values that are consistent with this leaf must be the same. So what the protocol is doing is actually it's partitioning the space into a bunch of monochromatic rectangles. So that's a very nice combinatorial picture. And that means that what you can prove, a simple theorem, if f of xy can be computed with c bits of communication, then that means this matrix, this is for deterministic communication protocols. Deterministic communication, that means this matrix can be partitioned into, at most, 2 to the c monochromatic rectangles. So why 2 to the c? Because there are at most 2 to the c leaves in the protocol tree. So if there is a protocol that computes this function f, so if at the end here they know f of xy, then it must mean that if you draw this matrix for f, and then you find the rectangles that correspond to the leaves, those have to form a partition of this space, and each piece in that partition is a rectangle and is monochromatic. The value of f in that piece is exactly the same. So, so that's a simple result. Very useful, and it allows you to prove lower bound. So actually, I'm not going to do it now. But for example, if you want to prove, suppose you want to prove, I claim that for the equality function you have to send n bits to compute equality. How can you prove that? So let me give you a hint. Just draw its matrix. So what is the matrix of equality? It's actually exactly the identity matrix, right? When the row and the column are the same, they're equal. And when the row and the column are different, they're not equal. So how do you prove that equality requires at least n bits of communication? Just prove that there's no way to partition this matrix into less than 2 to the n monochromatic rectangles. That's a claim. If there is a protocol with communication less than n, you could partition this picture into less than 2 to the n monochromatic rectangles. And I claim actually that's impossible. And it's not too hard to do it. You can try to do yourself, or look in the draft of the textbook that I might teach you. But the last thing I want to do is I want to show you converse. So converse to the theorem is also true. A partial converse is true. So it says that if fxy can be partitioned into 2 to the C monochromatic rectangles, then you might expect that this means that there is a communication protocol that communicates with C bits of compute F. But that's not true. In fact, that's too optimistic. But what you can show is this means that F can be computed with order C squared bits of computation. Okay, and well, it's 2:30, but I think 5 minutes is probably all I need, or less. So I'm just going to tell you the proof. We actually already saw the protocol that solves this converse. So I'm just going to tell you how to use it. You can probably guess because it's the only one that has square in it. So in fact, to prove it, so now I want to show you that if you have this matrix and it can be partitioned into 2 to the C monochromatic rectangles, then that means there's a protocol to find the XY entry using order C squared bits of communication. And the way I'll do this to you is, this is actually just the cliques versus independent sets problem, the first problem we talked about today in disguise. Okay. So let me show you why that's true. So let's define a graph. So suppose we have suppose F can be partitioned into 2 to the C monochromatic rectangles. I'm going to define a graph. Okay. So what is a graph? The vertices are going to be all the 1 rectangles. Okay. And the edges, I'll put an edge between U and V if the following picture happens. So I'll put an edge only if the 2 rectangles that correspond to U and V, so this is the 1 rectangle, this is the 1 rectangle. I'll put an edge if there's actually a common X input that pierces both of them. So if they have some row in common, I'll put an edge between. That's a graph. Okay, so each of these vertices corresponds to 1 rectangle. There's an edge exactly when they have a common row. Now I claimed that, so what are Alice and Bob trying to do? So Alice has this input X, which is the name of her row. What they really need to do is they want to find out if their common input XY, does that lie in a 1 rectangle or a 0 rectangle? Right? If it lies in a 1 rectangle, the answer is 1. If it lies in a 0 rectangle, the answer is 0. So they have, in other words, they actually just want to know, does their input lie in a 1 rectangle? So Alice looks at her input, it's X, and that pierces some subset of the 1 rectangles. But all of those 1 rectangles, they form a clique in this graph, right? Because all of them have this X row in common. So the definition of the graph ensures that for any 2 rectangles that are consistent with X, there is an edge between them in this graph. Okay, so Alice, can take her input X, and this is a clique in terms of this 1 rectangle graph. On the other hand, Bob has Y, and I want to claim that actually Bob's input, you can think of it as an independent set. And that's because, what does Bob see? So Bob sees this picture, and there's a bunch of 1 rectangles that he knows about, and they all have y in common. So they all have y in common. But if they have, these are disjoint sets that all have y in common. They cannot have any x in common. So if you have two rectangles that have y in common and they also have x in common, that means they intersect. That's the only way it can happen. This is the only way you can have both an x and a y in common. So these rectangles do not have any rows in common. The rectangles that Bob sees. So they're an independent set in this graph. There's no edge between any two of them. Okay, so what we have here is just an example of the Higgs versus independent set problem. And we saw that you can solve it with log squared n bits of communication, where n was the number of rectangles. Here the number of rectangles are the number of vertices. Here the number of vertices is 2 to the c. So if you just use the protocol we talked about in the beginning, you get here an order c squared. Solve this problem. So I'll stop there. Any questions? Yeah.
So these computations are with output 1 bit.
Yes. But everything I said, you can generalize to more than 1 bit. There will be a change to the theory. But for simplicity, I'm sticking to 1 bit. But you can take whatever I said and easily generalize it to more than 1 bit. Be a little more complicated. Instead of having both just 0 and 1 rectangles, you'll have other kinds of rectangles with other values. But you can understand everything in the same theory.
So in the case of more bits, at the end of the computation, Edison and Bob will obtain a common value.
Yes. Yeah, a common value which is more than a bit.
Can we say that only C bits of communication will be required given partition? Can we ever say for sure that only C bits of communication?
If you just have the partition,
Yeah.
This says that you can use at most order c squared.
Yeah.
But in general, there's no criterion that I know that's besides trying all protocols. And we do know, I should say, we do know examples where 2 to the c rectangles are enough to cover the matrix, and you need at least c squared bits to compute. So this is actually tight. So that's something we do know. It was proved recently by Kotar after months. That also gives a lower bound for the clique independent set.
All right, let's take a break. We're running actually a little bit late. The break will be like around 15 minutes or so. So we'll try to get back at 2:50. There should be coffee and refreshments outside here. So our last speaker, Dr. Mohammed Adali, will be have another announcement.
Another announcement is that all participants who have their presentations today can collect their posters during the break.
And remember, video abstract will be very nice. I mean, right now the talks are happening, but try to get some video abstract.